Look at this picture and tell me what you see. The correct answer is twins. It is hopefully clear from this picture that these two individuals are twin sisters. However, twin sisters are only twins because there exist two of them. If I showed you a picture of just one of these women and asked what you saw, you would certainly not answer that it was a twin. You would probably describe instead a somewhat unsettling picture of an older woman who does for leopards what Cruella de Vil did for Dalmatians. Just as twins are relationally defined, so are isomers. The relationship that we play up in all isomers is that all isomers have the same formula, but are different in some other way. Most of these differences result in isomers being considered as completely different molecules with different names, with one exception. This relationship between molecules can take different forms. The simplest is just when single bonds are rotated, conformational isomers. Conformational isomers are different than all the other isomers in that no bonds must be broken for them to interconvert, and they are actually the same molecule. Atoms may be connected differently as well. For example, 2-methylpentane and 3-methylpentane have the methyls at different positions. These are called constitutional isomers. Pause and draw these two molecules to convince yourself that they have the same formula but are not the same molecule. Again, 2-methylpentane and 3-methylpentane. Isomers may also have the same connectivity, but different orientation in space. At the end of Chapter 3, we saw one example of this as double bonds prevent rotation and lock groups on the two carbons, either on the same side or on opposite sides, same side being cis and opposite sides being trans. These were examples of stereoisomers. One special case of stereoisomers is where molecules are complete mirror images of each other, but are still not the same molecule. These are called enantiomers. The relationship between enantiomers is the same as the relationship between your right and left hands. This chart helps to relate some of the types of isomers, which we talk about in much more detail in the next two chapters. In this chapter, we will focus on conformational isomers and constitutional isomers, those shown in red on this chart. And we will talk in more details about stereoisomerism that actually results in different molecules in Chapter 5. In order for us to understand configurational isomers, it helps for us to have good ways of visualizing configurations and how they place atoms relative to each other. This is particularly important because some molecules will only take on certain configurations because of spatial constraints, and some will react very differently in different configurations. A Newman projection is a way that we typically think about the relationship between atoms attached to adjacent atoms. The nearest atom, typically a carbon, will be depicted as a point. Substituents will space themselves around the atom equally, and their bonds will come together and meet at the point, making a Y shape for tetrahedral atoms. The bond that we are looking at is behind the first atom, so we draw the second atom as a circle, again with its substituents spacing equally around it. These substituents have their bonds marked only to the edge of the circle. The Y shape for the front atom and the Y shape for the back atom can be rotated relative to one another to represent all the possible orientations around a single bond, with the orientation being shown having the lowest energy, because all the bonds are staggered relative to each other. Again, these Newman projections allow us to represent all the orientations around a sigma bond. However, this is most interesting every 60 degrees as we rotate between having the groups on the front and back completely staggered to completely eclipsed, and vice versa every 60 degrees. You can see ball and stick models of this with matching Newman projections right here. Notice that even when we mean to indicate groups on the front and back atoms completely in line or eclipsed, we draw them slightly off from each other so we aren't writing atoms on top of each other. The previous slides showed the rotations in 60-degree increments amounting to a half turn, and this slide simply shows the other half turn, again alternating between the highest energy, the eclipsed conformations where everything's in line, and the lowest energy where everything's staggered. I've mentioned a few times now that staggered configurations are lower in energy than the eclipsed conformations. This is because staggered interactions keep the bonding sigma orbitals as far apart as possible, while the eclipsed configurations lead to significant overlap between filled orbitals. You might be remembering back to Chapter 3 and thinking, I thought orbital overlap was a good thing and led to bonding interactions. That's a good thought, but remember, bonding interactions occur when filled and empty or two partially filled orbitals interact. Filled orbitals already contain negatively charged electrons at capacity and only repel one another. The strain between head-on repelling of orbitals is called torsional strain. Let's take those 60-degree rotations and plot the energy of each of them. The eclipse conformations are much higher in energy, and the staggered are at a minimum. The difference in energy is about 3 kilocalories per mole, or 1 kilocalorie per mole for each set of eclipsing hydrogens. Write that down. An eclipsed hydrogen-hydrogen costs about 1 kilocalorie per mole every time it occurs. The 3 kilocal per mole total difference in energy is called the rotational energy barrier. This barrier means only molecules with sufficient energy have, quote, free, unquote, rotation. This is not large, but at room temperature, only about 2% of ethanes have this energy. Before you lament the plight of the many, remember that any individual atom is just one collision away from having sufficient energy, and these collisions are constantly happening. If an ethane can't rotate now, it will be able to soon. The interactions between hydrogen in a staggered position is negligible, and the interaction even in eclipsed positions is relatively minimal. However, we could have all sorts of atoms besides hydrogens. Take, for example, this 1,2-dibromoethane. The bromines are now large enough that they will have interactions even when they are staggered but adjacent. The strain from the size of the bromines is called steric strain. Notice that if we plot the relative energies of 1,2-dibromoethane as it is rotated, the curve has a more complex shape. The lowest energy configurations are still the staggered ones, but the configuration with bromines anti or opposite one another is more stable than the configurations with bromines next to each other, which we call gauche. Similarly, the highest energy is when the bromines are on the same side, which you can see at the top. It's cis, where the other eclipse configurations that match bromines with hydrogens are far lower in energy. We can actually back calculate the cost of each of these interactions from the graph, as long as we remember that the cost of a hydrogen-hydrogen eclipse was about 1 kilocalorie per mole every time it occurred. In their plus or minus 120 degree configurations, there is one hydrogen-hydrogen eclipse interaction, and there are 2 hydrogen-bromine eclipses, for a total of about 6 kilocal per mole. Since hydrogen-hydrogen accounts for only 1 kilocal per mole, we know that 2 hydrogen-bromine eclipses account for the other 5, so about 2.5 kilocalories per mole each. The 60-degree structures only show gauche interactions and have a value of about 3 kilocal per mole. Write these down too. An HBr eclipse costs about 2.5 kilocal per mole, and a BR-BR gauche costs about 3 kilocal per mole. Use the same strategy to try to identify the cost of a bromine-bromine eclipse, and bring your answer to class. We can have these same considerations for long chains of atoms rather than just single atoms or groups. Regardless of what the groups are, generally anti-configurations generate the least strain, so our molecules tend to be most stable in zigzag lines rather than curled back on themselves. Hence, we tend to draw our molecules in zigzag lines. Nice work, us. While this is generally true, molecules will take on other configurations some percentage of the time, and can even be forced into higher energy conformations. The molecule shown on the left entraps a 14-carbon chain and forces it into an all-Gaussian conformation. This work was done by the Julius Rebick Jr. research group at the Scripps Institute, which specializes in creating large molecules with special spatial constraints. They have an interesting one to bind uranium from seawater too. In this chapter, or this lesson, we've learned how to draw Newman projections and use them to assess strain. In the next lesson, we'll apply that to three-dimensional structures that include rings.